Right, we're looking at Related Rates Worksheet 3. This is one of an older FRQ problem from College Board. A circle is inscribed in the square as shown in the figure. So we have a circle inscribed inside a square. The circumference of the circle is increasing at a constant rate of 6 inches per minute. So from here we know what value to assign this variable to, because we see 6 inches per minute. This is describing not circumference, but the rate of change of circumference. We see the word increasing and circumference. So we know that the rate of change of circumference must be equal to positive 6 inches per minute because we see the word increasing. So from there, we can just go ahead and assign the variable to the value in the problem. As the circle expands, the square expands to maintain the condition of tangency. So we're given some information that we need. Circumference is 2 pi r, area is pi r squared. For part A, find the rate at which the perimeter of the square is increasing. Indicate units of the measure. So if we want to find the perimeter of the square, we need to know how to find the dimensions. So we're not given the length of the square, but we do have something that's related that we can use. We are given that the radius of the circle is r, radius r, and radius r also happens to be half the distance of one side length of the square, simply because we have point of tangency. So we know that from end to end, the diameter of the circle is also going to represent the length of the square. So we're going to use that that relationship to help us identify an equation for the perimeter of the square. So the perimeter of the square must be equal to 2r, okay, or length, one side length will be 2r, which means all the side lengths will be 2r since this is a square. So then we can now create an equation that relates radius and perimeter, since this is the only information that's given to us. So if that's the case, then if we add up all the side lengths of the square, we have perimeter is equal to 8r. All right, we add 2 plus 2 plus 2 plus 2 equals 8r. All right, so let's see if we can map out how we want to solve for part A, which is finding the rate at which the perimeter is increasing. We're looking for dp dt. So to find dp dt, let's just go ahead and find the derivative and see what we're up against. So the derivative for p is going to be just 1 dp dt. The derivative for 8r will be 8 dr dt. So the idea is, if we can find out what dr dt is, then we can figure out what dp dt is, right? But to find dr dt, we need to kind of work through some more steps here, because we are not given the rate of change of the radius. However, we are given what the rate of change of circumference is, so maybe we can use this to help us get to dr dt, and then from there get to the rate of change of perimeter. Right, so let's see here. We know what the circumference equation is. So what if we find the derivative of circumference? So c becomes dc dt. 2 pi is a coefficient, it just stays. So the derivative of r is just going to be 1 dr dt. So we know what dc dt is, so if we can plug this in, 6 in for dc dt, then the only variable missing is dr dt, and then we can solve for dr dt, and then from there we can plug in to the dp dt equation to find the rate of change of perimeter. So let's go ahead and take those steps. So dc dt gets replaced with 6. It's equal to 2 pi dr dt. So to find dr dt, we're going to divide the 2 pi over. So 6 over 2 pi is same thing as 3 over pi. So that's dr dt, positive 3 over pi inches per minute. So now we can take the final step of replacing dr dt with 3 over pi, and then we solve for dp dt, which is 24 over pi inches per minute. Okay. All right, number 2. At the instant when the area of the circle is 25 pi square inches, find the rate of increase in the area enclosed between the circle and the square. So we want to find the rate of change of this shaded region between the circle and the square. All right, we first need to start off creating an equation that allows us to find the area of this shaded region. So if we think about this, the area of the shaded region we can find by subtracting the circle from the square, right? So I have an equation here. I have A, area of the enclosed is what we're looking for, area of the circle, so A sub c, and then area of the square. So the equation that we're going to use is, we know the area of the enclosed, the area of the shaded region, is equal to the area of the square minus the area of the circle. Okay, so we can use this to create an equation, and then from there we can evaluate the derivative. All right, let's see what else is given to us. At the instant when the area of the circle is 25 pi square inches, so let's go ahead and assign A is equal to 25 pi. Find the rate of increase in the area enclosed. So we're looking for dA dt for the enclosed. So I have dA sub E over dt. Okay. Indicate unit of measure. So let's see here. Let's go ahead and find an equation for A sub s, the area of the circle, area of the square, and then the area of the circle. So the area of the square is simply going to be length times width. So we know the length of it's going to be 2r for the square, and then the width is also 2r. So the area of the square is simply going to be 2r quantity squared, or 4r squared. Okay, I'll write that in. The area of the circle is simply pi r squared. All right. So then we can now create an equation that will get us to the area of the enclosed region. So area of the enclosed is simply area of the square minus the area of the circle. Okay, now we have something in terms of just one variable, and we can work from here. So let's make our next step. We want to find the rate of change of the area of the enclosed region, so dA sub E over dt. Okay, I'll put the sub E down here. So that means we're going to also find the derivative of each of these remaining terms. So 4r squared becomes 8r dr dt. The derivative for pi r squared is 2 pi r. So we bring down the 2, and the pi is just going to attach itself to the front. R to the first times dr dt. All right, so now we have an equation, a differential equation, to solve for dA dt, or the rate of change of the enclosed region. So now the only missing information is finding dr dt. Okay, so to find dr dt, let's see, dr dt is going to be the same as from what we have given here, since we know dr dt is going to be increasing at a constant rate. So we have a value to plug in for dr dt. So dr dt gets replaced with 3 over pi. The only thing missing now is the radius, right? How do we find the radius? Well, we know that the area at this moment in time is 25 pi, and we know the area of the circle is pi r squared. So then from here, we should be able to work our way down to find the specific radius at this moment in time. So we can replace A with 25 pi, divide both sides by pi, we get 25, take the square root, so radius is 5. So now we have values for radius and the value for dr dt, so we just plug those in. R gets replaced with 5, dr dt gets replaced with 3 over pi, and then the rest we can just simplify from there. So 40 times 3 is 120 over pi, minus the pi's cancel out, 2 times 5 is 10, 10 times 3 is 30, so 120 over pi minus 30 square inches per minute. We can find a common denominator, but this will be acceptable. All right, number 2. Suppose that a spherical balloon grows in such a way that after t seconds, v is equal to 4 root t cubic inches. How fast is the radius changing after 64 seconds? All right, so there's a lot of moving pieces here. Let's see if we can list out as much information as we can. So, all right, we know v is equal to 4/3 pi r cubed, so that's our equation. Okay, let's just go ahead and find the derivative, since we're trying to eventually get to how fast the rate is changing. We're trying to find dr dt, so we need to get to dr dt. So let's just go ahead and find the derivative of this equation with respect to time. So v becomes dv dt. 4/3 pi is coefficient, it just stays. R cubed becomes 3r squared dr dt. If we continue cleaning this up, the 3's cancel out. We're left with 4 pi r squared dr dt. And then if we want to find dr dt, we need to get to dv dt. Okay, so to get to dv dt, let's see what information that we have. We know that v is equal to 4 square root of t. So we can find dv dt using this equation. So dv dt, so v becomes dv dt. 4 square root of t is the same thing as 4t to the 1/2. We're going to find the derivative of t with respect to time. So we're not going to have to attach a dt over dt for this variable since time is the independent variable. So let's go ahead and find the derivative. We bring the 1/2 down. So 1/2 times 4 times t to the negative 1/2. So going through power rule, we have to also continue to subtract 1 from the exponent. And then dt dt, it just cancels out. It's going to be negligible here. So from here, we can find dv dt. All we need is to find out the time. So t is equal to, at the moment, after 64 seconds. So if we plug in 64 in for t, we can then solve for dv dt. So 4 divided by 2 is just going to be 2. 64 to the negative 1/2, the same thing as square root of 64 in the denominator. So 2 over root 64 becomes 2 over 8, which is 1/4. Okay, so we know dv dt is 1/4 cubic inches per second. So we can replace dv dt with 1/4. The only thing, all the other missing piece is looking for radius, right? How do we find radius? Well, we know that volume is equal to 4/3 pi r cubed. We can figure out that the volume at this moment in time is going to be 32 cubic inches, because at the moment that time is 64 seconds, we can find out the specific volume. So volume is simply 4 root t. So 4 root 64 is 4 times 8, which is 32 cubic inches. So at this moment in time, volume is 32 cubic inches. And if we go back to our volume equation, we can solve for r. 32 is equal to 4/3 pi r cubed. We're looking for r, so we can divide both sides by 4/3 pi, which is the same thing as multiplying by 3 pi over 4. And when we do that, we get 24 over pi. Take the cube root, and we get to our radius. Our radius is cube root of 24 over pi. So quite a bit of work is involved to get to dv dt and to get to r. But now that we have those, we can plug those in. dv dt again is 1/4. R gets replaced with cube root of 24 pi. It's 24 over pi. And then we just have to go through cleaning this up. So cube root of 24 over pi. We can divide all this over to the other side. And we're going to have to deal with the decimal. So plug this into the calculator one step at a time. We're left with 1 over 194.9, which is roughly 0.005 inches per second.